I have a PowerPoint.
Oh, okay. Turn on the projector.
Want me to put my sunglasses on for you?
Aloni, I was gonna turn this in, but I'm sure you don't want it to.
No, you can go. Turn this thing on. Oh, okay.
I can do it like this.
Yeah, it's-
They just have the plus down there.
Just down here.
That's the best you can do. Just scroll down. It shows 1 out of 6.
Okay. All right. So we'll just do it like this. It'll be easy.
Put the minus so it backs off a little more. That way you get the whole.
Okay. So good evening. We're gonna do the single crystal turbine blade, and I'm your instructor, Jake Handy. All right. So first time I heard of the single crystal turbine. First time like I looked up the single crystal turbine blade. Like first thing came to mind was Indiana Jones and the Crystal Skull, and I was like, that's kind of what I thought of it. Was like just a giant crystal. Could have been more wrong. So basically, what is the single crystal turbine? It's basically what Stephen and Jude and probably Elaine's going to say. It's basically them expediting the process so that you have a more condensed and pure turbine blade instead of having kind of like a turbine blade that when you look at it in the molecular level, it's kind of like a bag of Chex Mix. It's got like a little bit of everything and it doesn't all fit right. So they basically narrowed down the science, and this is what it actually looks like. Stephen was right. This end part, when they're doing it, it does create a pigtail, and they cut that off right after they finish the casting process. And so the purpose of it is basically to allow hotter temperatures in the turbine, which will allow the engine to run faster and hotter, aka faster speeds, better fuel economy. The advantages of it are basically allowing the technology of turbine engines to progress and hopefully like get a lot better than they are now, even though they're pretty awesome. And so the other advantage that it has currently is that it allows the lifespan of the turbine blades to be a little bit longer. It delays creep. Creep is still going to affect it, which in the end kills all turbine blades most likely. But the whole advantage, or at least one of the major advantages of this, is it allows to postpone creep on the turbine blade so you can get more bang for your buck later on. The two pretty much companies that make this is Rolls-Royce and Pratt & Whitney. Pratt & Whitney kind of patented it, and Rolls-Royce is kind of fighting them on the patent, from what I understand. But this technology was kind of like brought up right around the 1960s, 1970s, and it's just been kind of being improved from then to current. And then I just have a short little 7-minute video that I got off YouTube from Rolls-Royce. Should I play it or
No.
Yeah, go ahead.
will it link? No.
Oh, yeah.
I know. What's next?
Turn up the volume here a little bit too.
Why aren't you keeping it?
No, you have to shake it. There's an amazing component in the whole engine.
I'm gonna show you this whole video. Probably not.
Jet engines work by sucking air into the core and through multiple compressors. Squashed to a 50th of its volume, this air is forced into a combustion chamber, where it explodes with fuel to create a ferocious gas jet. This jet is met head-on by the turbine blades, spinning them so fast that each blade delivers the same horsepower as a Formula One engine. The job these tiny blades have to do is unbelievably demanding.
The blade exists in a fairly harsh environment. It has to rotate at about 10,000 revolutions per minute, the blade speed of about 800 miles per hour. The component itself operates at something like 300 degrees above the melting point of the alloy.
To operate at around 1700 degrees, they're designed not to melt.
Here you see the gas streams moving around the airfoil. At the bottom of the blade is the fir tree area, which is used to hold the blade into the disc. Above it you see the aerofoils with a peppering of cooling holes.
To stop the blade melting, Rolls-Royce designers used computer modelling to design a blade that has a precise pattern of tiny air passages throughout.
Here we see what the blade would look like if we didn't have it cooled. And you can see that there are some areas of red, which means that the component is too hot. We put a cooling system inside of the blade, which cools it down to safe levels, and that cooling system takes away the same amount of energy that would boil a kettle in a 20th of a second.
But even with the cooling holes, no ordinary metal would be good enough. That's where the company's Materials Research Laboratory comes in, creating new metals with exactly the physical and chemical qualities demanded by the designers.
To try and achieve the properties that the designers want, we will design some trial compositions of alloys with different recipes, different blends of the alloy constituents, and then we'll test those samples of different mechanical and environmental tests. And from that, we'll choose the best possible blends, which will deliver exactly the balance of properties that they require.
Using electron microscopes, the materials scientists can precisely analyze the microstructure of the alloy, checking that the crystal structure and the mixture of metals is exactly as intended.
We've got a team of research specialists, about 25 in a team here in the UK, and there are teams in Germany and the States as well. And we're trying to draw on all the expertise that exists in the academic network around the world, bring all the best expertise we can into Rolls-Royce.
Even a finely balanced alloy recipe isn't the most advanced technology in the turbine blade. To cast the metal into its complex shape, a unique process is used, and it's another very closely guarded secret. It's done at a purpose-built foundry in Derby, where one of the few people who knows the secret is casting engineer Owen Draper.
If you take a normal piece of metal and solidify it from being molten, you'd end up with something that looks a bit like a granite worktop. Lots and lots of little different crystals, all in different directions. That's not very strong because the different crystals, the joints and the boundaries between them, they just cause a weakness. So what we aim to do here is create a single crystal. Single crystal, no crystal boundaries, therefore it's an awful lot stronger.
The blade is made by growing a single crystal of metal into the correct shape. It's incredibly complex and demands a huge team of people working round the clock. But it starts with an intricate, hand-built model of the blade in skilled hands like Maureen Hankins.
I've been doing it on and off since '73. skill is you've got to be very dexterous, everything's got to be perfect, everything's got to be smooth.
The secret part is the way the molten metal is cooled through a spiral tube at the base of the mold. The tube prevents all but one crystal of solid metal from passing through, allowing that single crystal to grow throughout the mold. Imperfections could ruin the casting at any stage. Even the wax models are x-rayed by keen-eyed inspectors like Jackie Brown.
We're looking for defects in the core, i.e. cracks, chips, void. When it's sentenced to scrap, is thrown in half and put into the bin.
Yes, sir.
It's what they call investment casting.
Once cast, every single blade is thoroughly checked and checked again by eye, by computer, and by X-ray. Even then, they're far from ready. Each blade goes through another 4 days of precision finishing in the hands of machinists like Steve Ball.
We're all very good at what we make. We don't sometimes share it. It's not until you see Trent Fleet fly over. I've made mine good at that.
And because of the extraordinary demands on the blade, its dimensions must be accurate to within 1/10 of a hair's width.
We grind the fir tree to within 7 microns, which is a hell of a tight limit. It goes under a load of 18 tons that does. If we stretched it with 18 tons, regauged it, there would be nothing. Everything would be to the micron the same. There's no alterations in the structure. There's no cracking. There's no stretching of anything on there. And bearing in mind, you've got 96 of those in an engine set. Every one is like the first one. It's perfect. It's like a brand new baby. You treat it like that. That's why the focus of everybody in the shop's the same, whether it's 6 in the morning, 6 at night, 12 at night. Everybody's the same. The next one's always the most important because all the rest are good. Because we've never had one come back. You can't argue with that.
It's the skills of people like Steve and the cutting-edge technology that keeps Trent engines ahead of the game. But innovation is a risky business. Designing the Trent engine almost brought Rolls-Royce to its knees.
Okay, we'll see the rest of that movie. It's really an interesting movie. It's about how Rolls-Royce built a turbine engine. It's about an hour long, so we'll see the rest of that probably in a couple of weeks once we finish all of it.
13%.
Cool. Thank you.
Thanks, Jake. Jake, you basically had a video time for you.
Yeah. You had 7 minutes. 7 minutes.
Yeah. Let's do the next presentation.
Lane.
Mine's not as fancy as Jake's there. I don't have any.
You're still fancy.
Thank you, I appreciate it.
Here for you.
I'll be quick. I know you guys want to get started on the test here.
You're silly.
Thank you. All right, we're going to talk about the, my name's Tyler Lane, if anybody doesn't know, by the way. Talk about the single crystal blade. It was created out of necessity for the turbine engine blades. Needed to be higher temperatures than what they had with their original kind of casting that they had. So they came up with a form of casting to create the single crystal blade. It was created, it was found or discovered around the 1960s. There were some developers in Pratt and Whitney that had noticed a process that if you had a few bends in the molding or in the forms of mold that came off from the casting that came off at right angles, it would make the structure a little bit harder. And after messing around with that for several years, another one of their developers had come up with the helio channel that has a smooth continuous turn. that would create a natural substructure filter, which basically would pull out all of the grain imperfections down into that pigtail, and it would leave the actual blade itself one solid piece of metal with all the imperfections basically kept down on that pigtail. The pigtail would then be chopped off and just discarded. This created a much better material needed for the turbine engines that we have, and that's kind of the
Yeah.
So you kind of got an idea how that works now. And it's a heavily guarded patent, but we know that it's a method of vacuum forming, which what it is. They do it in a centrifugal centrifuge. And what that does, it throws all the weird stuff out against the sides of the helical, and then they have a vacuum that pulls it up through this helical. When it pulls it, draws it through the helical, it pulls one single crystal through, because it all kind of squishes through it works its way up. So it gets rid of all the junk and debris. And everything that's left in the helical is what's just discarded. So investment casting, as you saw the wax molds that they make there, and they can make those wax molds because they use a standard mold to make the wax mold. So each one of those is the same. Every one of them is the same. And then they cover it with a ceramic compound and then build that ceramic compound up. You saw them dropping like sand over it. But it's a ceramic material that adheres to the liquid that they coat the mold with. Then they put it in the oven and they burn off the wax. The wax just burns out of it. What that leaves you with is a perfect empty mold. And then they start drawing the metal up through that. So in doing that, they leave all the crud in the helical, and the rest of it pulls right up into the mold as a solid piece.
I'm guessing this is a very, very, very time consuming
Yeah,
process.
it is. Well, you heard the guy say it took him 4 days after the thing is made to actually finish it, so.
Well, I mean, grinding and stuff.
Oh, yeah.
I meant like pulling the metal,
Yeah.
like the helical.
Yeah, somebody's got to build all the molds, those ladies that were working there. They have to stick all this together and make it so that it will all work when you see actually mold something. Yeah, it's a lot of finishing, a lot of details. Each one of those little turbine blades, they're about $4,000.
Wow.
About $4 grand a piece.
Almost like 100 in each section, right?
I think it was 90, so about 95 or
Yeah, it was
96 or
95 to 100. Each
Yeah,
section.
and that's for stage,
Yeah.
on the high pressure stage, and then you've got the intermediate stage and then the low pressure stage on a Rolls Royce. So you've got all these different length turbine blades, and they're all different lengths, but they're all in the high temperature zones. In the high pressure turbine HPT area, they're all made like that. And once you start going further and further back in the engine, the temperature starts dropping because the structure of the engine begins to absorb some of that heat, and also some of that heat is lost through just running the engine, right? You're transferring heat into kinetic energy. So there's a transformation of the energy from heat into mechanical motion. So the temperatures start going down the further back in the thing you go. So it's quite an interesting process. But I'll show you that movie in a couple of weeks. We'll just take an hour. We'll just watch it. It's very good. It's a BBC program on how Rolls-Royce builds their engines, and they go down into some pretty small, dinky details. And in all these towns, these company towns in Connecticut, for instance, where Pratt Company is, and in Ohio, where General Electric is, and in this case, all over England, Rolls-Royce is there. Rolls-Royce is the premier place you want to work. You know, it used to be somebody else, but Rolls is a huge company, big industrial company. So that's like when you get a job in there, it's like.
It's a big deal.
Yeah, it's a big deal, yeah. And they're company towns, a lot of little towns where these plants are.
This
Kind of an interesting dynamic. You'll see, some of it's kind of hokey, but it's kind of cool. Okay, let me go get the test. Why don't you clear your minds and clear your tables, and we'll go ahead.
Good presentation, dude. Yeah, I think we should have presented it.
Yeah, we should have tag teamed it.
I have expected. Correct. And PT looks like a
Yeah, the LBC and the HBC, LBT and HBT.
VIG, variable intake, variable intake, inlet guide, VGB is variable guide, NVG is novel guide bank. And data bank is every single stage, temperature, and pressure. What's the sulfur one? What's the sulfur? What's what? QEC. Quick engine change. Hey, I'm learning something. Data? Isn't that like something you could game translator? You used your Walkman out? Data? 430 digital image. He had